Friday talks. So my understanding is this is our first in-person, wildly popular here in the room. But it's a nice day, so I'm glad to have made the trip and so forth. So I'll be talking to you mostly through the OWL. So we'll see how the eye contact works. So anyway, welcome everybody. I want to talk to you today about kind of more than just Python. I think that was the original talk, but kind of this philosophy of being able to keep up with technology, and part of your experience as a graduate student is in fact learning the technology and getting to the point where you can actually do your research. So it seems like when I was doing my graduate work, I spent a lot of time trying to figure things out before I actually got to actually answer my research questions. My name is Jeremy Daly. I'm an associate professor here. If you don't know me yet, I started here in systems in 2019, and I'm pretty excited to be here and share some of my experiences with you. So let's see, we'll get good advance on slides and everything. Okay, so today I want to talk about the technology and some of the tools of the trade, and you may hear a few debates back and forth on what the best tools are, and that's okay, right? Because that's not really, I'm not trying to be a champion of one or the other necessarily, but I do want to share my experiences and then give some examples. I also want this to be interactive if possible. So if you're at home and on the call, you can somewhat follow along with us. So I wanted to give these options up for you early, so you can actually get the system installed if you haven't already. And if you're familiar with Python, this would be pretty easy. If not, there's no requirement to do this in real time, but you may find it interesting. So there's kind of two options. There's like a really lightweight version where you can just install the Python itself and then the Jupyter Notebook on top of it, or you can get this Anaconda distribution that has everything included, but it's quite a bit heavier, right? So you're looking at almost a half a gig download. So I caution you to try to do that right now while we're trying to go through our Zoom call, because it may not make it.
Anaconda has R too.
And Anaconda does have R and an R editor and everything. So they are very inclusive in their approach. They sell themselves as a data science platform. So that seems to be a popular theme these days. So I've got a couple examples I want to go through. One is kind of introduction to Jupyter, and I'll introduce stats models, which is the heavy duty Python statistics calculator. And then I want to talk a little bit more about testing, specifically unit testing. So this is kind of something that is relevant for a systems engineer, and I want to highlight an example on how to do that, and then advocate that you consider implementing unit tests in a lot of the things that you end up doing. Whether it's in Python or not is irrelevant, but the framework I'm going to show you is capable of testing things that are not written in Python. So the theme here, technology is half the battle of graduation. You come in fresh and you have to be able to solve a really hard problem. And the reason those problems are hard is that sometimes the technology to actually take care of them aren't there yet. But like good endeavors, it builds upon the successes and capabilities of previous tools. And so a couple examples here, right? If you can understand like numerical methods, then it's easy to solve differential equations, right? And that's going to be the foundation of a lot of things like computational fluid dynamics or finite element analysis, right? Some very domain specific applications. PV technology is important in understanding how to develop renewable energy solutions, right? So this technology progresses. So if you're coming into your studies, you have to recognize and allocate a lot of time to get well-versed with the technology that your research is going to require. And programming, for example, is a skill that you have to build over time in order to really take advantage of what the computer can do for you as a tool, right? And ideally, you want the technology to be helpful in the end, right? It's a way to improve, improve the research output, or to make your life better, right? Pain reducers, so you can automate things that take a lot of manual effort and ultimately finish your job, right? So when I was in graduate school, I felt like I cheated because I was able to create macros to run a whole slew of different finite element analysis without having to actually change things manually and then run a program again. And so I would set this program to go on Christmas break, and 3 days later I come back and I have this, corpus of data that was created while I was doing other things. And my advisor at the time really thought I was productive, and I giggled a little because I was definitely taking advantage of the automation technologies that we have. So technology was a win for me in that regard. The command prompt here on the right is the example from the previous page where I'm showing the output of the pip install Jupyter command, right? And so this is an example of how in the command prompt, either on your Mac or your Windows PC, if you've got Python installed, what you would expect if you were to just install this Jupyter notebook. Okay, so now you're asking, well, what is Jupyter? Jupyter is a environment to really help you interact with the Python programming language. And so I'll show a few examples on that. Another piece of technology that I thought I'd mention just because I use it a lot is Git. And if you have any British persuasion, you would actually recognize that Git is a derogatory term, which I think is kind of funny. The guy who invented it is Linus Torvalds, who came up with the Linux kernel, right? So they're quite influential guy. But I wanted to break it down with these three topics of Git, GitHub, and GitHub Desktop, right? So Git is the actual core tool that does version control and comparing different pieces of code or information or text to each other and giving you the ability to create a workflow. It's mostly command line, but it's also multi-platform, so you can run it from almost anything. Then GitHub is an implementation of the server that uses Git that has been widely popular, and it creates a lot of value-add tools, and mainly because it's free, right? So a lot of open source developers and then closed source developers would use GitHub to share their code, work in teams, collaborate, and it did create an opportunity for a lot of distance collaboration. It was recently acquired by Microsoft, so I think the GitHub platform netted like $7.5 billion, which makes me think I should have had that idea when I was playing with Tortoise SVN back in my Linux days. And then GitHub Desktop is the graphical interface that actually interfaces with the GitHub repositories and executes all these Git commands to do version control. So I bring this up because the examples that I'm going to do today, I put on GitHub. And so there's a GitHub link that we'll get to that, let's see, where do I have that? Yeah, here's the GitHub link. It's under Dr. Daly Systems Engineering, right? So I just built a repository that I use for different examples from class, so you can actually see what we're talking about, and you can log in, and that's open and freely available to anybody who wants it. Okay, so let me back up. Jupyter Notebooks. Jupyter Notebooks are a way to interface with the with the Python kernel, which is what's going to interpret all of these commands. So Python is actually an interpreted language, which means you don't have to compile and run code. It just works interactively. And so we can build scripts, and we can build object-oriented programs, we can build GUIs, we can do all sorts of stuff. But for a lot of research and teaching, I really like using Jupyter Notebooks, and I'll show you why here in a minute. I also put a link here to the Atlantic that talks about the kind of the philosophy of what Jupyter embraces. And the title of it is Scientific Paper is Obsolete. And what it does is it advocates for this idea of an interactive environment online where you have data that gets processed real time and results are presented. So you'll see how that works. Okay, so I'm gonna stop the share of the PowerPoint slide and pull up this GitHub already. So in here, you should be able to see the start. And if you have your Anaconda installed, it will automatically create a link in your start menu, and you can start up the Jupyter Notebook. The background, you saw it had a command prompt that shows the kernel, and it will then use your web browser as an interface. So this is a little thing, and then I have in my documents, there's a GitHub and that systems engineering repository. And I'm going to go straight into the intro to Jupyter. Okay, so how do you get this onto your computer? If I were to navigate to the GitHub repository, on my laptop, so I inadvertently touch my pad sometimes, so forgive me on that. So this is the repository that I've put together, and I've got a systems engineering, and you can see here where it is online, right? So I'm on the GitHub webpage, and under the code menu, you can actually just download everything here as a zip file. So once that's downloaded, you can open this up, extract, and then you can run it from wherever you are. Now, this won't keep synchronized with whatever updates are there. This is just a snapshot from today on what's on that repository. If you wanted to track and keep up with things, you would actually check this out or clone it, and the GitHub desktop gives you the ability to do that clone if you're interested. Okay, so I'll pause here just a second, make sure everybody's happy. If we've got, if you're actually going along, and if you need me to go back or have a question, feel free to either raise your hand or unmute. I know Catherine can probably alert me if I'm ignoring somebody by accident. Otherwise, I'll try to keep up with that, with all of that. Okay, so that's how we got the program. I have this installed here in the GitHub. And so if I just click on this, it's IPython, IPYNB. So it's the Interactive Python Notebook is what this is. So if I click on that, it'll pull it up into another screen. So I want to show a few things that are pretty slick about this. I think this is fairly well maximized. Okay, so the core of this is this idea of a cell. And so if I come in here and double click on here, there's the actual code. And there's two types of cells that we're going to use mostly. The first is Markdown, and the other is code. The nice thing about Markdown is you can actually format documents with this. It'll look a lot like HTML, which they call a markup language. Markdown is just, I think, a play on words. But the idea here is these hash signs give you different levels of headings. And I can actually pull in our systems engineering logo and format it, center it up. I can even change the size. And then I can run that and I have a nicely formatted header, right? So this is kind of the introduction to Python and Jupyter. And these are the different data blocks that you would enter things into. And you can kind of organize your thoughts using this Markdown, include things like URLs and so forth. I can also hit Shift Enter and that will render it for us. Here's the link to that paper I was describing, and the links are live, right? So it just pulled straight up to the Atlantic, and here we're burning our papers, right? So, but if you read this, you'll see it talks a lot about what this Jupyter approach does and how it's kind of a more, or a different way of looking at things. So one of the things I really like about this is you have the ability to, in real time, to see the results of your code. And if you're doing data processing, you can visualize it. You can run things in sequence. So the logic and the build of these things. You can also have it import libraries and other more advanced features for you. But for now, I want to start with just kind of the basics with this stuff. So the first thing we talked about was Markdown. And Markdown is really nice because you can do other things than just text. So you can also render web pages, you can include graphics, and you can do mathematics. And so if I double click on here, you'll see how to get some of the different formatting. And here what I've done is I've actually rendered the actual commands, right? So this is the LaTeX format, and then you can see the actual example. So if I hit Shift Enter and go back, you can see I've got the quadratic equation rendered from those commands. And so when you print this, you actually have nice looking mathematics. You can do Greek letters, right? So A cosine omega t plus phi, right? So sine wave there. Integrals with limits. So here we have the principle of impulse and momentum. So you can see how powerful LaTeX is to render. And I'm pretty sure Microsoft Word now uses LaTeX to render graphics, mathematical graphics. So I highly recommend, as you're working through your graduate studies, to kind of learn that format and that syntax, and it will really help you in representing nice, clean looking mathematical representations of things. LaTeX has also become available online. So you can use Overleaf and have your own version control and collaborative document using LaTeX. So I've written a few proposals. My computer science colleagues tend to really enjoy using LaTeX because it looks like code. So again, another tool in your toolbox if you haven't used this already. Okay, Python is a calculator. It's a high-level interpreted language. It can do more than calculate, but we're engineers, and so one of the things we like is our calculators, whether they're on our phone. I had a TI-89, started out with a TI-85, was pretty proud of that. Figured out how to program it too, of course. But let's just go through a couple examples. So I'm going to go through these relatively quickly. I'm going to hold the shift, it'll be Shift Enter for each one of these cells. The version you have on, if you download it from the network, may have these already completed, but you can see how these get executed. So first, we'll assign these variables. And we can do things like addition, right? You would expect A plus B to give you 13 here, A minus B, right? Multiplication, floating point division, which is what you expect out of, kind of what you call division. Interestingly, because it's still a computer, when you get to the final digit, it's not a 3, it's a 5. But it also has provisions for things like integer division, right? So if you were teaching a 4th grader math right now, long division, you would do things like remainders, right? So 3 remainder 1 is what you'd expect. Well, that remainder is actually called a modulus. So you can see we get 3 remainder 1, and they decided to implement a function called divmod, which will give you both 3 and 1. So it's kind of nice. You can raise things to a power, right? So 10 to the 3rd gives you 1,000. And if you go the other direction, 3 to the 10th, 9,049. And if you don't remember which one goes which, is A the lower part and B the upper part, or which one is it? You can always look that up, right? So there's a help feature that's built in, and you can see that the X is first, right? So, and then things like square root, which you would expect a calculator to do, does not work. And so this is where all of my favorite friends who love R come in and say, see, that's why Python stinks, because you don't even have a square root. And I concede that is true. So I have to look at this traceback and figure out why can I not do a square root in Python. And if I look here, it says the name sqrt is not defined. Okay, what that means is that it doesn't know what it is. And it turns out that Python doesn't come natively with square root, but it has a math library. So in order for you to actually do a square root, you have to import the square root function from the math library. So if we import that, then you'll have access to the square root, and now we can calculate the difference. We can get all of the math functions in here by just using a wildcard, and then we can calculate, really fun square root a cosine times pi b, right? So pi is actually a built-in constant, so that's kind of cool. It can handle complex numbers, right? So I have the I as the imaginary number, right? The square root of -1. It also knows E, Euler's number, as 2.71, so that's kind of neat. And just for fun, we can show Euler's identity, which says that E raised to the I pi plus 1 equals 0. So this E to the -16 is essentially 0 for engineering purposes. My computer science colleagues will sometimes debate me on that. So anyway, if you're interested in understanding Euler's identity, there's a Wikipedia article on that. I don't advocate Wikipedia for a lot of things, but usually the math stuff is okay, at least for that cursory understanding. There's some other math functions that are kind of neat. You can kind of see if you list that library, it'll show you all the different things for the the arcsine and the hyperbolic arc cosine and so forth. So those are all the different math functions that come included in that math library. A couple of them, I have to remember what order things. So like the arctangent, right? The 2-argument arctangent, I don't remember which one is my y and the x. Right? So, is it y over x, so x over y, and which one it does. So using the help will usually keep that straight. And there's also other helps like this. And this is kind of like you would expect in something like MATLAB, if you've ever used that when you were an undergrad. So that tends to be a popular teaching platform. And there's very similar features that Python has compared to MATLAB. And then there's just an overall help, so you can see how to invoke that as well. Okay, so all of those, I don't think there was any manual typing you had to do, so you just execute those and see if they work for you. The next thing that I really enjoy using Python for is plotting. I have given up Excel for plotting a long time ago because anytime I had to redo a plot in Excel, I had to go through the exact same steps, and I started getting very frustrated with the repetition. And so what Python does is it gives you the ability to have a pretty high quality plotting library, and you can write a script that captures all of your steps, and then you just hit the go button if your data changes and you get a new graph. And it also has this kind of inherent save feature. Like if you save the Python script to generate the graph, it will generate the graph 3 weeks from now too, or even if you switch computers or Microsoft decides to upgrade your Excel for you. So I have run into that issue before. So we're going to use a program called Matplotlib. This is a pretty stable and robust plotting library. Its only drawback that I can tell is it's relatively slow. In other words, you wouldn't want to use it to plot real-time data. Let's say you wanted to see an instrument streaming data in live or CAN bus or something like that. Matplotlib won't keep up with that without exhausting your resources. So let's see what this looks like. We'll import this pyplot as PLT. So this is kind of the internet convention for that. And this gives a lot of MATLAB-like behavior. So if you ever use MATLAB for plotting, this is going to feel and seem very similar to that. All right, so this next block is just to create a list going from 0 to 10 of in 1/10 of a second increments, right? So I kind of have this this time block here, and I'm pausing because I need to exit out of here. Okay, when you see the stars on the side, that tells you that it's executing, and it'll just kind of set up this queue. So now everything's kind of flushed out there, so you should be able to see the times I had it hung on that help feature. You have to actually enter something to get out of that block. All right, so this is relatively long. We actually use a for loop and append a new value that we calculated. That's not very MATLAB-like or efficient from a coding perspective. So there's other libraries that will help with generating those faster. So one we'll introduce here is called NumPy. And NumPy gives you things like linspace, right? It's just linearly spaced between the upper and the lower and 100 samples. So we'll pull that in and you can see you get an array that goes from 0 to 10 every 10th of a second. So that's kind of slow. Okay, so I want to get a signal from this. Let's see if we can just plot a sine with it, right? So if I take the sine of this, I get this error. Again, my math library doesn't understand how to read an array. So the issue is I have to use the sine or the mathematical function that's tied to the numerical Python library instead. So if I run that, you'll see a sine wave. So those are all the numbers, and we can convert this into a signal, right? Multiply it by amplitude, frequency, phase, and so forth, and still come up with numbers to simulate something a little bit more. So now we've got this X and Y, or this time and signal value, and we want to see it, right? That's ultimately what we're going after. I'll calculate another signal so we can superimpose these things. So that's signal 2. And now we can actually plot it. So the plotting, when I do shift enter, plt.plot, right? That's the core command. And you see that there's times in the signal. We can put our signal or our marker type, label it, and so forth, and then show legends, X labels, Y labels, grids, right? And if you think about what you have to do in Excel to do this, there's all sorts of drop-down menus, blocks, and so forth, and none of that ever gets saved each time. So whereas this one, I can keep this in place, and it's basically going to give me the same answer every time, and I do it once, and I never have to worry about it again. And I could go change any of these signals, right? So I can come up here and change this amplitude to 80 units and replot this. It should look the same, except I now have an 80 for my overall there. So the other feature, if you look at the very bottom here, is I'm saving this figure as an example thing. And so from this Jupyter Notebook, I've actually produced a publication quality graphic in a PDF format. So if I think I have a link for this. I'll show you that in a minute. Let's put another signal on top of it. So you can see there's multiple signals. And then here's the actual link for the save fig. And this is, right, it doesn't pixelate at all, and you get pretty good rendering. So all of the styles and so forth, you can get the Greek letters and so forth on the side. All of that is kind of out of the box with this matplotlib. Here's the second figure that we just generated. And so you can have a script generate all the figures, and these can get imported into something like Word or Overview. If you are using Word, I would suggest using an EMF file or an SVG, Scalable Vector Graphics, for the best resolution. And this is what it looks like for the actual link. Right, I knew what I saved it like, so you can see how to make that work. Okay, so let's do something a little more related to probability and statistics. So here we'll just plot a normal distribution. So I've got a mean and a standard deviation. I can come up with kind of the x-axis here between -3 and +3 standard deviations. We'll make 1,000 points to sample from. And then here's the actual distribution itself, right? That's the closed form for the probability density function. And we can plot that out. And that looks right? I expected something like that. Again, we were able to represent this in its symbolic form as well using the notebooks. So these two can kind of tell that story about what you see and what the mathematical expression is and the code that generated it. Now, we're not going to always generate distribution functions with the closed form. For those of you who have kind of looked at the back of the statistics book and looked at reference distributions, you probably saw things like gamma functions and all sorts of symbols that are scary. So that's why we like libraries. So down here, I want to introduce the next kind of tool, which is the Scientific Python, specifically the stats module out of the SciPy library. So we're going to just import the normal distribution with this command. And I put some links that kind of show the different features that you can use out of those of that Scientific Python library. But we can add some other features, right? Like I want to annotate. One of the things that's kind of mathematically interesting about the normal distribution is there's an inflection point that's one standard deviation away. So I want to be able to highlight that and say, what do I mean by inflection point? And so this block of code actually replots this curve and introduces the inflection point, and actually shows where it is. So there's an annotate feature. And of course, this isn't something that you would necessarily know off the top of your head. Usually when I do these, I know that this capability exists, but I usually have to go to the reference example or the documentation to make sure I get the syntax and so forth right. So now that this is here, I can just run this, and I am highlighting where the inflection point is. So that's kind of a neat, completely programmatically generated. I don't have to drag and drop anything. So it will always come out the same way for whoever runs this code. And of course, it's saved in this PDF. So you can see right here when I click on this, there's a nice inflection point with the nested blue and black arrow, right? So that's kind of a slick feature. Zoom back out. Let's see, when using computers, variables and names sometimes get to be challenging, right? So let's say I want to write a program to describe a class of, to say fifth graders, right? So I'd come up with this variable and I call it class, and there's 45 people in the class, so I just want to say class is equal to 45. And I run this and it says, no, you can't do that. Well, it turns out that, class is actually a keyword in Python to create an object. And so when you see these keywords, that's one of those things you can't use. So none of these, false, none, true, and as, assert, and so forth. These are all reserved words that you can't use as variables. So that sometimes is a challenge when you come into a new language. You've got to kind of figure out what those are. Things that you may have written in a different language, say JavaScript, bring it over to Python, and now something doesn't work quite right. And it could be because of those protected words. There's other things that these following commands kind of show different things that are protected. A lot of times you'll see like an underscore, right? So you can avoid those. These are going to be commands that have been used from other libraries. Right? So as these tools get bigger and bigger, there's more and more words they have to use in order to represent the symbols. And so sometimes that there's conflict there. I always advocate for using kind of long descriptors with underscores or camel case. Kind of the bigger the better is when it comes to variable declaration in writing programs. So anyway, these are just a few examples of how to inspect your programming environment a little bit more. Last block I have here is Jupyter extensions. It turns out that even after all these years with all the writing, my engineering degree means I actually don't spell very well. So I have to use a spell checker. And Jupyter notebooks don't come natively with spell checkers, but there's an extension. So this has saved my bacon a few times. So this gives you an idea of how to install those. And So that kind of concludes this kind of introduction to Jupyter, some of the Python capabilities, just scratching the surface. So I'll open it up to questions and then move over and show a little bit on statistics capabilities. Good Friday afternoon. Everybody's kind of sleepy, getting excited for a warm weekend. All right, fair enough. All right, pandas and ANOVA. All right, so I pulled this example. It's relatively short, so I didn't want to spend too much time going through all of the statistics required. So I just wanted to give you a little bit of insight into some of the neat tools that are available. I actually used this example in the design of experiments class. So if you've had that class with me or are interested in it, this is kind of a flavor of what it looks like. This dictum is very, I think, appropriate. All models are wrong, but some models are useful, right? So we live in a day where there's a lot of information flowing out there, and I'm maybe a little more cynical than most, and I think everything's wrong. So I just hope that I can get some utility out of it. So one of the tools that we have in our toolbox is, in fact, statistics, and hopefully we can use these tools to help take all this data and condense it into a form where we can get some useful information out of it. So a little example here of a randomized block experiment. This actually came out of a textbook for the evaluation of penicillin based on raw materials. So there's 4 different blocks for 5 different blends, and there's trying to figure out the process for this penicillin, right? If there's differences that are significant based off of the raw material that comes in. And so you have this kind of structure to the data from this randomized block. So I want to show how to pull this data into a data structure that's in Python called pandas. And there are, it's kind of creative. I still giggle a little bit why they call it pandas. I always think of Kung Fu Panda, because my kids are that age where they enjoy that series of movies with Jack Black and the and if it doesn't work, then we always say that the pandas are loose. And so we have to go back. So anyway, pandas is a way for Python to handle these kind of large or intricate data sets, more so than just the native lists, and there's a lot of extra features on it. I'm not sure what this would be in R, if it's just, what do they call it? Is it like an array?
Like a tibble, probably.
A tibble, okay. So we'll see if that matches the definition here. Okay, so we're gonna import, before I do this, I'm gonna go up here and clear all outputs. So I'm gonna restart, clear all outputs, so you can kind of see the progress here. Okay, so Shift Enter will import pandas. We're going to call it PD for short. There's obviously some links to the documentation. And I'm going to take that data and enter it in. So I've got the different runs, the blocks, the treatments, and then the actual yield or the output here. And so it'll make a file-like object, and it'll write it to there, and we'll read that data in and create a pandas data frame, is what it's called. So now here's the actual data frame represented in the Jupyter Notebook. That's called the data frame. And you notice that it added this index on the left-hand side. Okay, so one of the powers of this is the ability to do groups and group by. And so if we group by treatments, you can come up with what essentially is the bottom of the table, right? So we take averages of all of those columns and group by those things. Same thing with the blocks, we can get the right side. So those averages will show that. The overall mean of everything there. So you can see the Y value, the overall mean was 86. And that's actually the same thing as our, what we call the grand average in this case. We can get deviations where we take the mean of each one and subtract off the grand average. And so if you recall from some of your statistics classes in the past, we tend to focus on deviations as opposed to absolute values because everything has a mean, right? And so we usually try to look at the differences from the mean. We can see the different parts of the table. Right here's the bottom for the deviations. We can do sum of squares, right? So these are, what's really neat is you can index these by column and do math on the entire columns. So here we're going to sum the squares. So we square everything first and then sum it. So we get a sum of squares total. We can calculate degrees of freedom by subtracting off the grand average for that. Figure out the number of blocks by the group by, degrees of freedom for the blocks, number of treatments, and then we can start doing sum of squares of the different blocks and treatments. Right, so these are all quantities that when you open your stats book and you read through how to develop like an ANOVA table, you would have to do these calculations. Right, so degrees of freedom, and then finally the residuals for that sum of square. When you put all of that together, it basically accounts for everything because there's no duplicates in this case. All right, so this next block is kind of a way to iterate through this at a little more like in depth. It kind of shows the iterative nature that you would do if you didn't have the power of the pandas, right? So these are the things that kind of go on underneath the hood. And then I'm going to kind of fast forward through here, some more residual calculations, the mean square error of the different quantities. And then finally, if you're doing an analysis of variance, you calculate the F statistic. And we compare that to a reference, right? And so in this, right, so all of these things would make sense had you been following along for 5 pages in a textbook with this. So I'm just basically entering numbers into the calculator at this point. But I want to show you how to do, you kind of leverage these imports, right? So I want to look at the F distribution and calculate those p-values. And the p-value is essentially the strength of the conclusion. All of those numbers will go into building an analysis of variance table. And if you have this, this is a rendering, right? So here's how you can, in the Jupyter Notebook, create a table. So all those numbers we just calculated would then get inserted into this, and finally you represent those p-values, and you would be able to draw a conclusion that there is a significantly difference between the blocks, but not between the treatments, right? So based off those p-values. Right now, if you've actually looked at this and thought to yourself, man, that is a lot of work for such a simple table. Why would I ever use Python for this? Because there's probably a lot easier way or an automatic way just to generate an ANOVA table. And the answer is yes, there is. So what I want to do to introduce that is this idea of a model, right? So we're dealing with linear models for linear statistical models, which basically says we have a mean, a treatment, a block, and residuals. So that's what the model that we're trying to actually analyze is, using this analysis of variance tables. And so the R language was actually very well tuned for this. And so some good practices that come out of R are available in Python. You thought this would be adversarial, huh? So stats models is the package, right? So if you look at this, this is kind of the Python module that gives you a lot of the kind of the advanced functions that you would expect from a data processing engine. So highly encourage you to look into that. Jump to through this. Basically, I have to create this model using an R-like syntax, and then I can create an ANOVA, a linear model for the ANOVA, and the answer just gives me an ANOVA table. So I don't have to do any of that stuff that I showed earlier. It was quite boring and almost they put people to sleep. So all of those calculations that took place earlier are basically built into these two lines. So that's quite nice. The danger, of course, is you've got to know what those two lines do, which is why I went through the detail before. And then there's different types, right? So here you don't have the mean square. This part does it with to include the intercept as well. So, and then finally, I want to show what the p-value and what that means. So we'll plot the F distribution. And so you can see one of the distributions here gives our p-value of 0.047, and the other one gives a p-value of 0.338. So you have a little bit, right? This is your reject region. So when you have a lot of shaded blue, you probably can't confidently reject that hypothesis. So anyway, I wanted to show kind of just crack open the hood a little bit on some of the power that you get from using something like stats models, and just show it applied to an analysis of variance table. So that's the second part of what I want to talk about today. Any questions before I move on to my last topic?
Very nice thought.
All right, last topic. Let's see if I can pull this up. We did Jupyter, and do you see the full slide? No, lost the mouse. Unit testing. All right, unit testing is often neglected in college because you want to get the job done, and sometimes you're not getting graded on kind of the maintainability of your code. But over the years, I've learned that good unit testing is paramount to keeping track of what's going on and being able to revive code that you may have written in the past. So it is actually a systems engineering concept, right? So you got your class of D diagram, and right here in the middle, right above your, in your implementation, you should have unit tests. So I want to go through what a unit test looks like today and how you can actually use it to improve the robustness of your code. And as things get more complicated, the need for testing becomes more and more important. Okay, so the example I'm going to use to motivate this is I'm going to create a function. I've actually already written it, but it's relatively short, so I'll describe it. And we're going to read data in from a controller area network off of a truck. And it has a value for speed in there, and I want to interpret it and show that speed in miles per hour. We're going to use the SAE J1939 standard to decode it. And I'm going to look to see if we can't create some environments or some conditions where this would, where we can handle the exceptions correctly. So the motivation here, we did some testing with the autonomous trucking attenuator. Hopefully you can see the video coming through. If you look, you'll see the steering wheel is actually not measured, so it's actually in the right now. And this is the power of the vehicle, and you can see the lead of the vehicle in front. And we turn the corner to try to follow through here. And you get a set about some right? So it stopped. And so we were creating these graphs, speed versus time, and comparing different data sources for those speed records. So we had a GPS antenna that we put up there, we had the system log file, and we had our CAN traffic, or J939 traffic from the powertrain. And so the function I'm going to show you is actually interpreting the raw bytes from the network on the powertrain and converting it into speed. Okay, so let's see if I can pull that up here. Escape out of that. And I have it in Visual Studio Code. See if it remembers where I was last time. Probably not. Open recent. Come down here, intro to PyTest. So it's on that same repository that I indicated earlier. And there's a program here called speed conversion. Okay, so this is the actual code. So I'm calling this function convert CAN bytes to speed. Gives you a little bit of description. So I read in the bytes in those positions. It's actually the second and third position in the data stream. And I use this structure to unpack that and put it into an integer, right? So I've got a value from 0 to 65,535, which is 2 to the 16. Convert it to kilometers an hour, which is according to the SAE standard, just dividing it by 256. And there's actually a range for this, right? So I have to check to see if this is out of bounds. And if it is, return none, right? So this is the actual standard here. You can see I'm looking for wheel-based vehicle speed, which is this suspect parameter 84. SPN 84. Oops. Will show so here's my data range. So anything within that data range is valid. If it's not, it's invalid, so I return none. So that's the motivation behind this. And then I convert from kilometers an hour into miles an hour and return that value. Okay, so that's the function. I would think relatively straightforward. You can implement this in Excel or something like that. But what I want to test for is how does it respond to the different types of CAN data that I send to it? And do I get the nones correctly and so forth? So I've created a unit test. So this is called testspeed.py. And I'm using a framework called PyTest. And PyTest looks for any function in file that starts with the word test. And then it goes through, and if it sees the word test, it says, I'm going to execute that, and so forth. So there's a special command called the assert command. And basically what it does is if you assert, one thing is, assert a Boolean, either true or false. If you assert true, then it moves on to the next. If you assert false, it raises an exception and stops the test. So that's pretty cool. So I'm going to import this function from speed conversions that I just made. And I'm going to start out by testing all zeros. Okay, so I'm going to take this CAN data, I'm going to put all zeros into it as the input message, try to convert it to miles per hour, and then assert, right, check to make sure that I actually did get 0 out, right? That should work. Then I'm going to see if I get 120 kilometers an hour, or what ends up being 75, close to 75 miles an hour. I'm going to make sure that that works, and then I've got a couple other here that I'll show you. Okay, so to make this happen, I need to run, here's my, I should be able to run, so change directory to intro, PyTest, and it's Python -m PyTest, and I use the unit test directory. Okay, I actually failed. And the assert says that 74.564 is not equal to 74.5645. So my test criteria here is actually too strict, too tight, because I'm using floating point math. The precision on here actually matters. And so when it does this exactly equal to, it doesn't work. So I don't like this. I want to make sure I get close enough. So what I'm going to do instead is put two asserts in here. So assert speed miles per hour is greater than or equal to 74.56 and speed mph is less than 74. Okay, if I save that, now I should be able to run this test again. Hey, look at that. So it passed, right? So now I've got some confidence that I can handle zeros and I can handle 75 miles an hour, right? But there's other things I want to look at. So for example, let's try this test, which is all, so control one comment that. This is all F's, right? So if I did all zeros, now all ones, binary ones, and this should convert to out of range, right? It's above, right? If you think about it, it should be 255 kilometers an hour, whatever that is, and that's actually out of the range. So save this and run the test again. I am expecting to get none. Well, it failed. Okay, why did this fail? Okay, it says assert minus some small fraction here is not equal to none. So it didn't actually come back with none. So now I'm looking at my function as potentially, there's some issue here. So let me look at this. And I go through here and this is strange. So I'm going to look at that. I'm using a little h, which is an integer that's 2 bytes long, but it's short. So what happened is I should have used unsigned short integer. So if you know the difference, one can handle minus signs and the other one can't. I use the one that handles minus signs, but according to the standard, there is no minus sign, right? Speed's a positive value. So I actually used the wrong format string in this unpack statement. So this should actually be a capital H, right? A little detail that it looked to work fine, right? At first. But if I had good unit testing, I can uncover these little small mistakes. One character off, one capitalization off, and this would have fixed it. So let's hopefully this works now. So if I change my code, now I should be able to run the test again, and it looks like I passed all three. So now I'm actually kicking back a speed of none if I get all F's, which is what it should be. And then finally, go to this test. I want to try a couple things with bad data. So here I have some malformed data. I just put 1 byte in. So I'll save that. So part of your job as a test engineer is to kind of come up with these crazy cases to make sure your code is robust and it's not going to die on you when you feed it things that aren't quite right. So I'll run the test again. It failed because it needs a 2 byte buffer. So what I would have to do in this case is do some exception handling. In Python, what I would do is I would do what's called a try except block. So try except, and the exception here is in the struct error. And I would just, if that fails right there, I would just return none. Right, so basically my answer now, if I wanted to be a little bit better, I would put a debug statement and say why it returned, but at least I can get through and leave that none handling to something else. So that gets saved, and now I pass. Last one, and I will be finished, is, put in the wrong data type. All right, so here I'm putting in an integer of 120. Save that and run it. And it fails because it doesn't know how to do a 1 to 3 or actually pull bytes out. So then I use the same approach up here. So I can do a try. And then this type will stay, I'll be explicit. So only do this if it's a type error. And then return. So we got that fixed, and now the test should pass. So anyway, a quick example of unit testing, very much an important aspect that is oftentimes ignored by your subject matter experts and your domain engineers. As a systems engineer, I think it's really important that you emphasize unit testing. So these types of things stay down at the lower part of the beam. They don't creep their way all the way up to the system and integration test. It's a lot less expensive to fix them at the unit level than it is at the high end. That concludes my presentation. I hope you guys saw a little bit of insight into the utility and power of Python. For all of you R lovers, I like R2. I just don't have any experience with it. Thanks.